Let's go, boys. We made it to day 5 of 30 minutes of problem solving day. I'm very impressed with myself, okay? It's kind of crazy. So, basically what we're going to be doing today is because last time we kind of got stuck on numbers 23 and 24. We didn't know where to go. I did get a hint on number 23. And basically today, what I wanted to do, because I did say I was going to finish the AMC 12A last time, is I'm just going to go over the solution for these ones because I didn't want to waste any more of you guys' time watching me just stare at the problem for like 20 minutes. So essentially, I basically looked at the solution, I worked through it myself, and now I'm ready to present to you guys the solutions, okay? I am not, however, going to go over problem 25 because, like, it's kind of hard. Also, like, Osman Nall already made a very good video walkthrough of it, so I thought it would be kind of redundant. So check him out if he's like really good, right? Like check him out if you're interested. But like he makes like IMO and like AMO walkthroughs and stuff. So he is a very good resource. Okay. So why don't we get started with problem 23? Okay. So essentially when I was doing it, right, like I kind of got the idea that you do have to do out the algebra, but I did miss one kind of thing. So I will show you how we get there and we'll get the solution eventually. So first step, let us do out the algebra. Very fun. I love algebra. God dang it, I hate algebra. So essentially we gotta find g of z first. So that's just like z plus a over z plus b, plus a over z plus a over z plus b plus b, and this just simplifies to z plus a times 1 plus b. Okay, or d times 1 plus a. Yeah, okay. Over 1 plus b times z plus a plus b squared. Okay. That makes sense. Okay, and now the next thing we gotta do is we gotta find g of z, and that's gonna be nasty. So we got 1 plus a times 1 plus a z plus a times 1 plus b over 1 plus b z plus a plus b squared. This whole thing plus a times 1 plus b. So let's just do the numerator first. I don't think we want to like bog ourselves down with the denominator too. So essentially, we could ignore this thing, right? We could just multiply it out and then ignore it. So we got 1 plus a squared z plus a times 1 plus b times 1 plus a, right? And then this side becomes a times 1 plus b squared z plus a times 1 plus b times a plus b squared. Okay. So essentially, these things are pretty easy to combine. You just factor out the a times 1 plus b, right? So that becomes a times 1 plus b times 1 plus 2a plus b squared, okay? And then this one, you just add them. You got 1 plus a squared plus a times 1 plus b squared times, whole thing times z. Okay, so now let us do the denominator, and then eventually we should be in good shape. So the denominator is like basically the same thing, except with 1 plus a b over here times 1 plus a z plus a times 1 plus b. And then we have the denominator, which is 1 plus b z plus a plus b squared, whole thing times this, a times 1 plus b. Okay. Is that right? Let me double check. No, what? It's times a plus b squared. Okay. There we go. So if we simplify this, we basically get 1 plus b times 1 plus a z plus 1 plus b times that, right? So we can factor out the 1 plus b, and it basically becomes 1 plus 2a plus b squared z plus a times 1 plus b squared plus a plus b squared squared. Okay. So essentially, this is the denominator, right? This is the denominator, this is the numerator. And essentially, in order for this to equal z, you have to have this is equal to 0, which is the part I didn't notice, right? Like, I didn't notice that you could just set this to 0 and that to 0, and that's the only way for it to work, right? But essentially, what you do is you set this to 0, you set this to 0, and then this has to equal this for them to cancel out, and you're left with z, right? So essentially, we could just write that out. We got 1 plus b times 1 plus 2a plus b squared equals 0, and we got a times 1 plus b times 1 plus 2a plus b squared equals 0, and then we got the other thing, which is a times 1 plus b squared plus a plus b squared is equal to a times 1 plus b squared plus 1 plus a squared. Okay, that was a mouthful, holy moly. But essentially, from the first one, we can see that b is either equal to negative 1 or 1 plus 2a plus b squared is equal to 0, right? So let's try the first one, right? B is equal to negative 1. then this one's also satisfied. We could basically ignore this one because it's like the same as the first one. And then essentially we get like this stuff cancels out, right? So you're left with this, and then this simplifies to a plus 1 squared equals 1 plus a squared, which is the same thing, right? So any a would work for this one. Okay, so b equals negative 1 definitely works. Then the next thing we got to do, a plus 1 squared, or a plus b squared squared, okay? And now the other option is you got 1 plus 2a, right? Like a is a complex number and it's magnitude 1, so 2a will have magnitude 2 and it's anywhere around the circle, right? So essentially we could rotate this around this point, right? So we want to maximize or minimize b, right? So minimizing b is clearly just to put like a right here, right? So then like this distance is as short as possible and b is equal to negative 1, right? b squared or b is equal to I, right? Because you want I squared to equal negative 1. Or your other option is to do, you got 1, and then make this whole thing straight. So you got 1 and 2, and then b would have to equal root 3i, right, in order to equal this thing. Oh, never mind. In the other case, it would be b is equal to negative 1, which we already checked. So if we got root 3i for b, we can actually plug it in just to make sure it works, right? Over here it would be a minus 3 squared is equal to 1 plus a squared. Let's check it out. A squared minus 6a plus 9 is equal to a squared plus 2a plus 1. And that simplifies to negative 8a is equal to negative 8. A equals 1. So essentially we got an a for our b, so that means root 3i also works. So we got negative 1 and root 3i. And anything in between would not be maximum or minimum, right? Because we can see that this thing rotates around. It's not going to be smaller or bigger than 1 or root 3. So our answer is simply root 3, which is the biggest one, and 1, which is the smallest one. And you do root 3 minus 1 is equal to our answer. Very nice. And our answer is C. Let's go. Okay. Number 24, like, I basically had number 24 solved. I just didn't realize that the way to maximize the area of a quadrilateral is to make it cyclic, which kind of makes sense, right? Because, like, cyclic is on a circle. It's, like, pulling it out, kind of. So, I should have known that. Cyclic basically is the way to maximize the area of a quadrilateral with a given side length. So, once you know that the quadrilateral has to be cyclic, right, then it's pretty easy, right? Because essentially you know that 21 times your in radius is equal to the area of the thing, right? Area of ABCD. And then for a cyclic quad, the area is just equal to this, hold up, root s minus a times root s minus b times s minus c, s minus d. And guess what formula this is called? That's right, Brahmagupta's formula. It's a very nice formula. And we can just plug in here to solve for r, and we are good. So our semi-perimeter is 21, and then we do 21 minus 7 minus 14 minus 12 minus 9, and that just gives us, all those do it out, you got 14 times 7 times 12 times 9, root of that, and you can factor out our 7, very nice, left with a 2, you can factor out a 3, or no, 3 over here, and then this is still 12, okay, then you can factor out a 4 from here, and then this becomes a 2, wait, what, hold up, am I trolling? Yeah, okay, that's right. And essentially the 21 cancel out with a 7 and 3, and you're left with 2 root 6 is equal to our answer, and we get our answer is C again. Dang, both of them are C. Interesting. With Lily 22 was C also. Dang, 3 C's in a row. If you get 3 C's in a row in 2011, you are a very lucky man. And also I guess, dude, I keep forgetting that I'm not editing this, god dang it. But like, basically, 25, you guys can check out Osmondall for his solution. Alright, so how much time did we spend? Let's see. We spent 8 minutes doing that. So we have 20 minutes to work on something else. And a lot of you guys asked me to do like the 2018 February contest silver problem teleportation, so I will do that. And let us see if we can solve it from scratch in 20 minutes. Probably not, so I'll continue it next time if we don't finish, but we'll do our best. 20 minutes on the clock. Let's do it. 20-minute timer. Alright, very epic. So, one of the farming chores Farmer John dislikes the most is hauling around lots of cow manure, okay? In order to streamline this process, he comes up with a brilliant invention, okay? The manure teleporter. I need that kind of invention, god dang it. Instead of hauling manure between 2 points in a cart behind his tractor, he can use the manure teleporter to instantly transport. Okay, you know what? I found out that with USACO problems, it's probably the best to just read the input format first. Okay, so first line contains N, and then your ith line contains AI and BI, and I'm assuming AI is just a teleporter, right? Where's AI and BI? Let's see. What? Dang. Did they not? Okay, I'm assuming AI and VR are the teleporter endpoints, right? Okay. Okay, you know what? I should actually read it. Okay. So essentially, the first endpoint of the teleporter is x equals 0. Oh. I see, I see. So, okay. So this just has the different piles that need to be moved, and then essentially you want to find out where you want to put the teleporter. Okay. I see. So, um, we basically want to minimize the D. Okay. I see. So in this case, let's just draw it out. We got our number line, right? We have -5 to -7. We got -2 to 7. And we got -3 to 10. Okay. -3, -2, 7. And we got -5, -7. Okay. So essentially, we want a teleporter that starts at x equals 0, and then, okay, so I guess if he's going from -2 to, or -3 to 10, this teleporter would only help him if it goes towards the 10, right? If it's closer to the 10 than just walking there, right? Um, yeah, so essentially you put it at 10, then you have to go, oh, it's saying the minute, okay, so you want to give the minimum one, okay. So if you set y equals 8, right, then essentially he only has to walk 2 for this guy, right? He goes from -2 to 1 to 0, -2 to 0, so that's 2, and then he goes 1 left, which is 3. Okay, so 3 from that one. Then for -3 to 0, you go 3, and then you go 2 to the right, so that's +5. And then for -5 to -7 is just 2. Okay. So essentially, we want to find a teleporter that minimizes this distance. So let us see. Well, this is actually kind of interesting. How would you even start with this? Well, it basically tells you that any solution in this range would be optimal, right? So that basically suggests that. Does it suggest anything? I mean, it suggests that like you could basically just say put a teleporter between these two cows, which basically limits the number of locations we had to test, right? So that's good. So let's just pretend that we're testing every like possible place to put the teleporter, right? So you can put the teleporter here, right? And essentially that would result in no benefit for these guys, right? And then no benefit for anybody, right? Okay. Um, so we could think of it as trying to maximize our benefit. Okay. Then this one would not benefit anyone, right? Huh. I guess, okay, so I guess we could think of it as in the teleporter only matters to the cows that are going from left to right over it or from right to left over 0, right? You can't go backwards, right? You can't go from Y to X. Yeah, okay. So, hmm. Okay, anyway, so we know that this doesn't really help anybody. Then if we put it in between -3 and 7, then we know it doesn't help anyone still. Okay. I feel like this test case is not very good for this because, like, yeah, because it doesn't have anything going from right to left over the 0. So how can we do this one? I'm pretty sure it involves just going through each possible location and then just updating that in O of n over one time. What's n here? N is, yeah, n is 10 to the 5, so you had to do it in O of n probably, or O of n log n. So what else could we do? Well, what do we even have to update when we go between stuff, right? Well, okay, let's say we moved this teleporter from here to here, right? Then, like, this guy, who used to be helped, right, will actually not get helped, or actually, huh. Well, okay, so this guy would potentially get helped more. Like if you do from 8 to 6, it doesn't change anything. But this guy, for sure, adds at least 3, right? Adds 3 to this guy, and then if you move it back another one, then okay, so it does change between here, right? Because essentially, like, as you go more, or as you go closer to 0, you're not even helping these guys at all. So I guess it's not just like one possibility within it. Okay. Huh, why don't we start it at 0, 0, right? So let's just say the teleporter didn't do anything, right? Then essentially there are some people who, if you move the teleporter right, would be negatively benefited, I guess. Well, they can't go under 0, is what I'm thinking. Okay, well, okay, let's just ignore all the people who are going backwards over it, right? So the only people who we do care about then are the people who are going from left to right over it, right? Then essentially we would only want to move this endpoint right, right, because then it would help the people who are going right over it. So let's just say, how right do we want to move it though? That is the question. Okay, so once you move it, so if you have like two, if you're in between, if there's only two guys that are going right over it and you go in between them, then no matter where you put it in between, it's not going to change anything, right? Because if you move it right, it adds one to this guy, but it subtracts one from this guy, right? But what happens if you had -1 and like, I don't know, 11, right? Then every time you move this guy right, both of these guys get less, but this guy only gets subtracted once, right? So, or this guy only gets added once. So essentially moving it right would be good because you're getting less, right? So eventually you would move it to 10, and then at that point, if you move it right one more, then these two guys would increase, and then this guy would decrease by 1, which is not good. Okay, so essentially, what we want to do is if you have 3, you want to put it on the middle guy, right? If you have 2, or like an even number, you just want it between the middle two guys. And then you can calculate that, right? Dang, I don't think that's too complicated, right? And then you just do it for the other side, and then you just figure out what the maximum of the two sides are. Wait, that's not even too bad, right? So you essentially just want to find all the guys who are negative, right? And then, like, if the product of the two endpoints are negative, that means they cross over 0, right? Are any of the starting points on 0? Oh shoot, they're not necessarily on 0. Okay. So what do we got? I mean, they could be on 0, is what I'm saying. So if it's on 0, well, okay, I guess it still doesn't really matter because then you could still figure out whether it crosses left or right. I mean, you can just go through each one and just see if it crosses left or right. Okay. Um. Okay, so what we're gonna do is we're gonna have like right crossing, right, RC, and we're just gonna store the right endpoints, right? So 7, 10, 11, right? And then essentially you just find the median, right? And then you calculate and then you just calculate the cost for that particular setting the teleporter to that point, right? Then you also do the same thing for left, right? So if you have like a 4 to -5, right? Then you would basically then you would put -5 here, right? And then you would find the median of all the left guys and put the teleporter there, right? Is that right? I think that's right. Okay. So I think that makes sense, right? Because if you're in the median, moving left or right will not decrease your thing. If there's too many guys to the right of you, then moving more left or moving right will actually improve your score, right? Because you're decreasing it for all the guys to your right and increasing it for all the guys to your left. So I think this makes sense. Let's code it up. How much time did we spend? Okay, we have 10 minutes to code it up. I do not know if this is possible, but we will see. Like the code, I think the hard part about this one is actually noticing how to solve it, right? But this shouldn't be too bad. Or teleport, okay. All right. So essentially we got our using namespace we got our int n, and we got our, do we even need it? Yeah, I don't think we even need it. So RC, RC 100, oh, let's just do a vector actually. Vector int RC, okay. And vector int left C. I don't know why I put the C, but whatever, it looks cool. LC, okay. And we will include vector. And we will also include fstream. Bruh. There we go. So we do, always put it underneath. If stream fin teleport.in, and then upstream out teleport.out. And essentially what we want to do, what do we want to do? Okay, so we got a fin n, and then for int I equals 0, I is less than n, I plus plus. So if it, basically right crossing means that it starts on the left or equal to 0, right? So if, we should probably do left and right, or start and end, okay. Int, what do they call it? A and B, okay. Int A comma B, Cn A, Cn B. So if A, which is the starting point, is less than or equal to 0, right? And B is greater than 0, right? Then it will benefit from having the thing move to the right, right? So in that case, you want to do rc.pushback B, okay. If A is greater than or equal to 0 and B is less than 0, right? So that means it crosses left. Then we do lc.pushback A, okay. Or pushback B, okay. So now essentially what we want to do is, what do we want to do? So now essentially we want to sort our RC, right? RC.sort, right? And then we want LC, or I forgot how to do this. We got to do this. Sort RC.begin, RC.end, okay. Include algorithm. And then we want to do sort algorithm. There we go. LC.begin, LC.end, okay. So now we just take the middle and then we find the cost. So how do we find the cost is the question. Oh, but the point, oh my god, I'm trolling. Oh, wait, this doesn't actually work, does it? Because if the teleporter becomes so bad that there's no point using it, then they'll just go directly, right? Huh. Well, that's annoying. Hold up. Yeah, because not everybody actually has to use it, is what I'm... Huh. That is whack, okay. I guess we have to have like a stop using point, right? So essentially if 0 to that, so if 0 to 2, negative 2 is bigger than that, then it just stops using the teleporter, in which case it doesn't actually impact it to move it more left. In which case it would be good to move it more left, right? Huh. Well, that actually changes things. Okay, let us think a bit more. So essentially, once you, okay, so you have to like keep track of where those points end up. Well, I guess those points are literally just twice the number, right? So once you get to twice the, twice your b, right? Once you get to twice your b, then it stops counting. But how do we keep track of that? Wait, how big are, okay, so the integers are pretty big, so you can't actually like go through all of them, right? But Well, I guess the only special points are -2, like twice a -2, like -3, twice a -3. And what do we do at those special points, though, is the question. Okay, so basically your whether it's adding one or subtracting one can only change at one of those special points, right? So essentially what we want to do is we want to keep track of those special points, right? And then we'll just go from left to right through those special points, and if we hit a special point, we just check is it increasing or decreasing, right? And then every time we reach the end of a decreasing section, then we want to check every time we reach the end of a decreasing section, we want to check if it's actually our minimum number, right? Okay, so let's try that again, right? So this is technically still right. We also want to push back twice of it, right? And we want to push back twice of it. And essentially we'll just go through it, right? So 4 into I in RC, right? And we have to keep track of how many guys are going right? Or no, we want to keep track of whether we're adding one or subtracting, right? So originally we're subtracting for every single guy to the right of us, right? Choose my changes, okay. So what does that mean? So essentially we had to start at our int decrement is equal to negative RC dot size, right? So once you start at like 0, 0, there's no decrement, right? Or well, okay, well in this case, yeah, at 0, 0, there's no benefit, is what I'm trying to say, right? So we essentially have to have our int benefit is 0 originally, right? And then essentially, for each time you move right 1, you're decrementing by all of the guys on that right side that are crossing over, right? So we basically go through, we go to the first guy, and essentially, do we have to keep track of whether it's actually an endpoint or not an endpoint? Because once we reach one of those twice as much, then we actually have to like take it out, or we have to like change the decrement, right? Because essentially it starts at n, right? But eventually once you get past a bunch, those things get flipped, right? So instead of adding to our decrement, they're actually subtracting from it. But then eventually they don't contribute at all. So we basically start with negative, then we add 2 every time we pass something, and then we have to subtract 1 every time it goes out of range. So how do we do that? Maybe we should have like a separate thing for these guys. Endpoints? End usefulness, I don't know. Vector int end re, okay. And we'll have our le, okay. I don't think I'm gonna finish it today, but I will do some more a little bit. Let's see. re, le, okay. Sort all these boys. And I should probably sort these guys backwards then, because we want to go from closest to 0 to farthest from 0. So we'll do greater. And we'll do greater here. re.end and le.begin and le.end. And we should probably just have like it's kind of like a 2-pointer, right? So essentially just take the least one. So you'll have one looking at RC, you have one looking at RE, and then if the one in RC is past RE, then you actually look at the RE one. So we'll have int PRC is equal to 0, and int PRE is equal to 0. So so once you get, so essentially it doesn't make sense to go past the last RC, right? Like it doesn't make sense to put the teleporter past the last guy. That just doesn't make any sense. So essentially what we'll do is we will go for while PRC is less than PRC is less than RC dot size. Okay. So what do we do? If RC PRC is less than RE PRE, then we actually look at it, right? And then we look at the RC PRC, and essentially we find how much gets decremented to our benefit when we reach there, right? So essentially our benefit, okay, we probably have to keep like int prev location, right? How much we've kept track of, right? Okay. So benefit is equal to decrement times how much we moved, right? So that would be times RC PRC minus our prev, right? And that would be plus or minus equals, right? I guess that should be positive then, right? Because decrement increases our benefit. Okay, so that's good. And honestly, I think we will continue this next time. And I think, yeah, we're done with our time. So we will continue this next time. I hope you guys found this helpful. I kind of enjoy this series, dude. This is kind of fun, just like doing daily problem solving stuff. So if you guys have any suggestions, leave them down in the comments. As always, if you enjoyed the video, leave a like and subscribe for more. Hopefully, we'll get through teleportation next time, and I will see you then. Okay, bye. Alright, you guys gotta watch me awkwardly turn off the screen. Hold up. Alright, now actually bye. Okay.